Okay, our last two attempts to find the integral of gravitational field between 2 points led to some pretty ugly results, although it would be feasible to resolve those and work them out. It really wouldn't be worth the time, especially when we're trying to introduce the whole topic. So we didn't complete those. We're going to complete this one because it illustrates how, if we choose the right path, we can get relatively simple integrals. Okay, so you can think about it. The gravitational force is an inverse square force. Its magnitude depends on r. Its direction is the direction of theta, wherever theta happens to be. So a treatment in terms of circles and straight lines seems to suggest itself. So we're going to do this. We're going to go from the first point. Now it was R1 theta 1 and R2 theta 2. Since I'm going to use theta, it actually looks like I never actually did use theta. I thought I was going to use theta, but I didn't. But I'm going to use alpha and beta instead of theta 1 and theta 2, but they have exactly the same meaning. So my path is going to be divided into two paths, okay? And we can always do this. The first path is just going to be around a circle centered at the origin. In other words, a circle of radius R1, okay? And it's going to go from angle alpha to angle beta, okay? Angular position alpha to angular position beta in polar coordinates. And then our second is it's going to go a straight line from here to here. Okay, straight line in the direction of the vector of the angle beta from R1 to R2. Okay, so the first part of the curve that I've labeled C1, and I'm doing that in one color, and I'm doing the C2 then in another color. The C1 curve is going to be described simply by R of t equals R1 cosine Ti plus R1 sine Tj for t between alpha and beta. Okay, and you can verify this is a type of a parameterization that should be very familiar to us, so you can verify that that works. And our C2 is equally simple. We're going to use t. I could have parameterized it just in terms of r, but I wanted to be more general, so I used t. I'm going to say R of t equals t times the cosine of beta times I plus sine beta times j. Now you can recognize that as just a unit vector in the direction of the angle beta. So it's just a unit vector in this direction. And we multiply that by t. And we let t go from R1 to R2. So when t equals R1, we just have t times R1 times a unit vector in this direction, which means a vector from here to here, so that's going to be our first point. And when t equals R2, we have a vector from here to here. So the points at the tips of those vectors will trace out this path. Okay, well on C1 the integral is very easy. Now intuitively we know that the gravitational force is directed toward the center, and this is a circle centered at the center, so that the tangent direction, the direction you're moving along the circle, is always perpendicular to the force, meaning that you're going to get no work. Okay, that F dot ds is going to be 0. But we're going to actually write that out here and verify it in terms of the symbols. So ds is what? Well, it's dr dt times dt. Okay, that's your change in position. Okay, and again, just a differential. And if we do our dr dt, we find that we get a negative sign here and a cosine here, so we get this, all times dt. Okay, so that f dot ds, well f, remember in ij coordinates, ij components, is just this. And here, developed a habit of real carelessness that I need to do something about. That should be an R1 to the 3 halves. So here's our F function that we've seen already, and yeah, speaking of omissions, it's a negative. But anyhow, it's this, and it's going to be dotted with our ds. And look at what happens. We have a cosine t here and a sine t here, a sine t here and a cosine t here, R1's on everything and a negative sign here. The dot product is going to give us 0. So we conclude that over past C1 f dot ds equals 0. And this is going to be true for any R1 alpha and beta. Okay? So it's true for any path along any circular orbit of M1 about M2. And if we assume that M1 is much greater than M2, then M2 will, if it's given the right velocity, orbit M1 in a circle. So it's not going to take any energy to maintain that circular orbit. There's going to be no change in velocity in that circular orbit, and that's really convenient because that's why our satellites stay up. Now they're generally in elliptical orbits. You got to generalize this a little bit, but this is calculus class. And we're not going to pull a whole lot of that in. This is a multivariable calculus class. We're not going to pull too much physics into it. Okay, but physics students will see the connection. Now, on path C2, well, let's just do the details. Our ds vector is again our dr dt times dt, and our dr dt in this case, well, it's just t times this. This is just a constant vector, so it's just this. Okay, so our dr dt is this. We multiply that by dt, so that our f dot ds is f dot, well, this thing that we got here, and integrating f over the curve C2, of course, t goes from R1 to R2 because that's how we parameterize the curve. Okay, well, f is just the negative g m1 m2 over r squared times r. Okay, and if we plug all that in, I didn't do all the details of that, but if we just plug the f function in there, and I guess I should write out the f function again so we know what is being plugged in. It was clear in the context of class. But f is just negative g m1 m2 over quantity x squared plus y squared to the 3 halves, and now it's going to get hard to read because I'm writing over things. That's to 3 halves times your xi plus yj. Okay. So when you dot f with this, what do you get? Well, you get cosine of beta times the I component here is going to give you cosine beta times x. Sine beta times j dotted with the yj is going to give you sine beta times y. The rest of these terms are just going to come right through, and you just need to write it out and see, but it's very clear that this is what you're going to have. Okay? So, comes this integral. But of course, x is what? Along this curve, x is t cosine beta. Okay? X is the I component of your position. Y is t sine beta. So replacing x and y by these expressions, we get this. Okay? And down here, we get what we see here. Okay? So that when we multiply all this out and go to simplify it, down here we're going to get a t cubed and again, do the algebra yourself, it's very straightforward, times cosine squared beta plus sine squared beta to the 3/2. In the numerator, we're going to get t times cosine squared beta plus t times sine squared beta. So we're going to get t times cosine squared beta plus sine squared beta. So cosine squared beta plus sine squared beta by the Pythagorean identity is 1, so we just have 1 here, we have 1 here, and all we end up with is dt over t squared, and the antiderivative of that we'll use the antiderivative, negative 1 over t, evaluated from R1 to R2 because t goes from R1 to R2, and what do we get? We get this. Now, again, work out the details, but they're very straightforward. And remember that we've seen this before. It's just our del F at the R2 beta point minus del F at the R1, then it's R1 alpha, not R1 beta. Again, you can sort that out and verify it, but these examples show you quite a bit about the mechanics of applying the line integral to an f dot ds. You'd have similar procedures for an f dot m ds. Okay?